Welcome back. In this video, we cover subset selection. Subset selection is the process of choosing a subset of relevant predictors from a larger set. The goal is to build a simpler model that predicts well and is easy to interpret. Why would we not want to use all available predictors in a model? There are two main reasons covered in the text. First, when the number of predictors p is large relative to the number of observations n, ordinary least squares tends to overfit to the noise in the data rather than the true underlying signal. And second, least squares includes every predictor by default, so there's no way to automatically drop variables that are not useful. Let's start with best subset selection, the most thorough of the four methods. Best subset selection evaluates every possible combination of predictors. For each possible model size, one predictor, two predictors, and so on, it finds the best model of that size, then compares across sizes. Here's how best subset selection works. In the first step, we start with the null model M0, which contains no predictors. Then, for each model size k from 1 up to p, we fit all p-choose k models containing exactly k predictors. Next, for each k, we keep the best one, mk, where best means smallest residual sum of squares, or equivalently, largest r squared. Once we have m0 through mp, we select the best overall using a prediction error criterion, such as CP, AIC, BIC, adjusted r squared, or cross-validated MSE. All of these criterion are covered either later in this video or in other videos. Let's walk through an example with p equals 3 candidate predictors, x1, x2, and x3. It's unlikely that the exam will ask you to implement the actual algorithm, but it's a good way to understand the steps and internalize the concepts. Here, with best subset selection, we evaluate every possible combination. We start with the null model M0, which contains no predictors, only the intercept. For k equals 1, we fit all 3 choose 1 models, each containing exactly one predictor. In this case, the model with x2 has the lowest RSS at 280, so M1 equals the set containing x2. For k equals 2, we fit all 3 choose 2 models with exactly 2 predictors, which includes x1, x2, x1, x3, and x2, x3. The model with x1 and x2 has the lowest RSS at 195, so M2 equals the set containing x1 and x2. For k equals 3, there is only one model, which includes all 3 predictors. That model has an RSS of 180, so M3 is the full model. Finally, we compare M0 through M3 using the Bayesian Information Criterion, or BIC. We'll cover this exact formula later in the video. Even though M3 has the lowest RSS, the BIC penalty for the extra predictor makes it slightly worse. M2, with predictors x1 and x2, achieves the lowest BIC of 8.8 and is selected as the final model. In total, we evaluated 8 models. With only 3 predictors, this is very manageable, but the number grows exponentially as p increases. The downside to best subset selection is its computational cost. Best subset selection must evaluate 2 to the p models in total. For p equals 10, that is about 1,000 models, which is manageable. For p equals 20, it is over 1 million. For p equals 40, it exceeds 1 trillion. In practice, best subset selection becomes infeasible for large p, which motivates alternative subset selection methods. The first alternative method is forward stepwise selection. Forward stepwise selection is a much more computationally efficient approach compared to best subset selection. Rather than searching all possible subsets, forward stepwise selection starts from the null model and greedily adds one predictor at a time, always choosing the variable that most improves the fit. In terms of the algorithm, the first step in forward stepwise selection is the same as in best subset selection. We start with the null model M0, which contains no predictors. Next, for each k from 0 to p-1, we consider all p minus k models, that include one additional predictor not already in the model. For each k, we select the best of those p minus k models based on the smallest RSS or largest R squared and call it mk plus 1. We repeat steps 2a and 2b until all predictors have been added. Finally, from the sequence m0 through m-p, we select the final model using a prediction error criterion, similar to the criterion used in best subset selection. Let's walk through an example with p equals 3, x1, x2, and x3. We start with the null model m0, which contains no predictors, only the intercept. Step 2 begins with k equals 0. We consider p minus k, which is 3 minus 0, or 3 models, that each add one predictor to m0. In step 2b, we pick the model with the lowest RSS. That is, the model with x2 at an RSS of 280. So m1 equals the set containing x2. Now for k equals 1, we consider p minus k equals 2 models that each add one of the remaining predictors to m1, which contains x2. Step 2b, adding x1 gives an RSS of 195, which is lower than adding x3 at 240. So m2 equals the set containing x2 and x1. Now for k equals 2, we get p minus k equals 1, so there is only one model to consider, which adds x3 to m2. In step 2b, that model becomes m3 with an RSS of 180. Step 3. We select the best model from m0 through m3 using a criterion like BIC. Even though m3 has the lowest RSS, the BIC penalty for the extra predictor makes it slightly worse. m2, with predictors x2 and x1, achieves the lowest BIC and is selected as the final model. Compared to best subset selection, forward stepwise selection only needs to fit 1 plus p times p plus 1 divided by 2 models in total. For p equals 20, that is just 211 models, compared to over 1 million for best subset selection, which is nearly a 5,000 times difference. However, because forward stepwise selection is a greedy algorithm, each step makes the best local choice. It is not guaranteed to find the globally best model. A variable added early may block a better combination from forming later. In practice, however, it still tends to perform well, so the computational efficiency gains may be worth the trade-off. Now let's take a look at backward stepwise selection. Backward stepwise selection works in the opposite direction as forward stepwise selection. It begins with the full model containing all p predictors, then iteratively removes the variable that contributes least until no further removal improves the criterion. In terms of the algorithm, the first step in backward stepwise selection is the reverse of forward stepwise selection. We start with the full model MP, which includes all p predictors. Next, for each k from p down to 1, we consider all k models formed by removing one predictor from the current model nk. For each k, we select the best of those k models based on the smallest RSS or largest R squared and call it mk minus 1. We repeat steps 2a and 2b until we reach the null model. Finally, from the sequence m0 through mp, we select the final model using a prediction error criterion, similar to the criterion used in the other methods. Let's walk through an example with p equals 3, x1, x2, and x3. This time, we work our way down. We start with the full model M3, which includes all 3 predictors. Its RSS is 180. Next, we consider k equals 3 models, each formed by removing one predictor from M3. In step 2b, removing x3 gives the lowest RSS of 195. So M2 equals the set containing x1 and x2. Now we consider k equals 2, with each set formed by removing one predictor from M2. Removing x1 gives an RSS of 280, which is lower than removing x2 at 320. So M1 equals the set containing x2. For k equals 1, there is only one model to consider, Removing x2 leaves us with the null model. In step 2b, that becomes M0 with an RSS of 500. Step 3. We select the best model from M0 through M3 using BIC. Just as in our forward stepwise example, M2 with predictors x1 and x2 has the lowest BIC and is selected as the final model. Notice that backward stepwise also fitted 7 models, the same count as forward stepwise. Here, both methods also arrived at the same final model, though that is not always guaranteed. In terms of strengths and weaknesses, backward stepwise selection is similar to forward stepwise selection in that it is computationally efficient, but it is not guaranteed to find the globally best model. The best subset, forward stepwise and backward stepwise selection approaches typically produce similar but not identical results. Hybrid versions of these methods sequentially add variables, like forward selection, but also remove any that no longer improve the model, combining the benefits of best subset selection with the computational efficiency of stepwise methods. Now that we know how to generate candidate models, we need a principled way to choose among them. That is what model selection criteria are for. As we saw from the earlier examples, to determine the best model from subset selection, we used criteria beyond RSS and R-squared. This is because RSS decreases and R-squared increases as the number of features increases. So, from a selection of models with varying values of P, the model with all predictors will always have the smallest RSS and the largest R-squared. While these measures may indicate a low training error, they may not accurately reflect a low test error. To better estimate test error, we need criteria that adjust for the number of predictors, P. Before introducing the formulas, let's define the key variables used for model selection criteria. D is the number of predictors in the model, including the intercept. N is the sample size. And sigma hat squared is the estimated error variance. Now that we've defined the key variables, let's look at the first criteria, Mallows CP. ISLR uses the first formula on the screen here, and Freeze uses a different but equivalent formula. Both formulas will penalize the model for having more predictors and will identify the same model as having the lowest CP, although they might yield different numerical values. Note that if sigma hat squared is an unbiased estimate of the true error variance, then CP is an unbiased estimate of the test mean squared error. The Akaike information criterion, or AIC, has the exact same formula as CP in the context of ordinary linear models with Gaussian errors. The syllabus states that AIC is used in the context of ordinary linear models, so for exam purposes, CP and AIC are equivalent. The Bayesian information criterion is similar to AIC, but replaces the factor of 2 with log of n. For large values of n, BIC applies a heavier penalty for each extra predictor than AIC does. This means BIC tends to select simpler models than AIC, especially as the sample size grows. Let's work through an example using the Akaike information criterion to select the best regression model. This is from the Society of Actuaries sample questions. We have a data set with 100 observations, 6 predictors, and a response variable y. 3 ordinary regression models have been fit. Model 1 uses only x1. Model 2 uses x1 and x2. And Model 3 uses all 6 predictors. The table shows each model's residual sum of squares and residual standard error. We need to use AIC to select the best model. Before diving into the calculations, notice 2 things. Model 1 has an enormous RSS compared to the other 2, like, wow, this is a huge RSS, but too bad it's a bad fit. Models 2 and 3 have very similar RSS values, even though Model 3 uses 4 additional predictors. This hints that those extra variables may not be adding much predictive power. To solve this problem, first recall that the AIC formula is RSS plus 2D sigma hat squared, all divided by n, where d is the number of predictors, sigma hat squared is the estimated error variance from the full model, and n is the number of observations. The best model is the one with the lowest AIC. First, we calculate sigma hat squared. Since Model 3 is the full model, we square its residual standard error to get 89.4575. We're also given that n is 100. For Model 1 with a single predictor, plugging in the values gives us an AIC of 1,838.42. Model 2 uses two predictors. Its AIC comes out to 91.84, dramatically lower. Model 3 uses all 6 predictors. Despite having a slightly lower RSS, the penalty for the extra predictors gives it an AIC of 93.93, slightly higher than Model 2. Model 2 has the lowest AIC at 91.84, so it is the best model. Adjusted R-squared modifies the ordinary R-squared to penalize for the number of predictors. The formula is 1 minus the ratio of RSS over n minus d minus 1 to TSS over n minus 1, where RSS is the residual sum of squares and TSS is the total sum of squares. In this adjusted R-squared formula, d counts only the slope coefficients. It does not include the intercept. This is different from the d in CP, AIC, and BIC, where d includes the intercept. Also note the direction. Unlike CP, AIC, and BIC, where lower is better, a higher adjusted R-squared indicates a better model. An alternative to analytic criteria is to estimate test error with validation-based approaches, such as cross-validation. There are a few advantages to this method. The first is that they provide a direct estimate of the test error with fewer assumptions about the underlying model, such as the estimate of the error variance. The second advantage is that they are computationally feasible with modern computing. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.